Hello everyone, my name is Minxiang. I'm from Georgia Tech. Today I'm going to present the work of a 65nm image processing SoC supporting multiple DNN models and real-time communication trade-off via active critical neural network controllers. And in today's presentation, I'll first talk about computation communication trade-off, especially on various image processing IoT platforms, both its motivation and a generic platform model. Then I will discuss architecture and circuit design details of the proposed SoC. Then I will show chip characteristics and measured results. And finally, I will draw conclusions. Now let's first talk about computation communication trade-off. Conventionally, wireless image processing IoT device design can choose either to process image locally on the edge or transmit the data remotely to the cloud. To choose the right strategy, the quantitative information of relative communication cost versus computation is required in design stage. However, in the real environment, communication cost is not constant. Variations in local environment, wireless channel, sensor network, and so on, we all play important roles of how much energy and latency it takes to transmit the data. As a result, it is highly desirable to have an alternative strategy between edge and cloud-based method that is able to smartly and dynamically trade off between computation versus communication. For example, when communication is costly, more image processing should be implemented locally and vice versa. This way, system-level performance, such as energy efficiency and the process latency and so on, can be significantly optimized. This slide provides a generic wireless IoT platform model for self-optimizing edge-cloud trade-off. This model consists of three major building blocks. First, a computation module to provide an edge-cloud pipeline scheme to trade off edge computation workload with cloud data transmission workload. Then, a communication module to always track smallest possible communication costs, adaptive to wireless channel conditions. Finally, an optimal policy controller to adjust both computation pipeline and adaptive transmission in real time. Now, let's discuss SoC architecture and circuit design details. The figure on the left shows a system architecture, both SoC in the middle and the peripherals around it. At peripherals, we have camera, power management, optional external DRAM, programming interface, and so on. In the core, besides necessary modules such as frame buffer, preprocessor, caches, and so on, there are three major modules for edge cloud-based image processing. First, we have a processing element array. This processing element array is to provide reconfigurable deep neural network acceleration pipeline for image processing algorithms. Then we have an on-chip adaptive transceiver. This is to achieve data transmission with real-time, low-cost on-chip adaptation to wireless channel conditions. Finally, we have an actor critical controller, which features self-learning, low latency, low overhead system control. Now let's talk about the circuit details of these three major modules one by one. First, DNN Processing Pipeline. The DNN analysis of several popular topologies are shown on the left. On the x-axis from left to right, it is deeper and deeper DNN layers. On the y-axis, it is normalized data volume in blue and accumulated number of operations in red. From the figure, we can clearly see monotonical tendencies of increased DNN operations and decreased transmission volume along with processing depths. This has provided a straightforward scheme to trade off between computation and communication by controlling processing depths. To provide a DNN processing pipeline and account for various DNN topologies, we have designed a reconfigurable P spatial array. In the 3x3 P array, each P's input and output can be connected to one of the four neighbors. Such an implementation provides a fine-grained control over workload distribution and data flow optimized for diverse DNN structures. Besides PE array for DNN pipeline, individual PE is also reconfigurable for various DNN layer patterns. The PE circuit is shown on the right. It has in-out buffer, configuration, and instruction decoder, and 8 computation threads. In each thread, there is an ALU, 1 KB SRAM with retention mode, a shift register, and 2 input selection muxes of VLU. This slide will show 3P configuration to address major computation patterns in DNN layers. The first is fully connected layer. Each thread acts as an output neuron whose input are shared and weights are local. All memory banks are in active mode. A maximum of 8 neurons operate in parallel in each PE. The second is convolution layer. Compared with fully connected layer, all threads share weights from SRAM global bus and receive input from local shifter register to compute filtering at various locations simultaneously. 7 out of 8 memory modules are in retention mode to maximally reduce static power consumption. Finally, the sparsely connected layer. In this configuration, one thread is for indexing and the rest threads for computation tasks. And now the second major building block is adaptive transceiver to have energy-efficient communication with external hub. A digitally reconfigurable data rate and channel-aware transceiver is designed on the same SoC and demonstrate the effectiveness of computation communication trade-offs through adapting to various data rates and channel conditions. The data rate control is achieved by changing the clock rate from 40 kHz to 10 MHz in 256 steps using an 8-bit control. The error correction code can be enabled by one control bit that turns on 84 Hamming codes. From the digital baseband, 3 bits of I amplitude control and 3 bits of Q amplitude control controls how many legs of the RF DAC would be turned on, while 2 bits of LO control generates appropriate local oscillator phases. The power delivery subsystem consists of reconfigurable RF DAC based power amplifier and a tapped capacitor matching network with reconfigurable capacitor banks. The RF DAC-based power amplifier combines DAC, mixer, and power amplifier operations in a single module through a digital-friendly architecture that switches on and off different legs of the module and can support higher-order modulation schemes such as 16-QAM or 64-QAM. The output power control is achieved by adjusting a capacitor bank. Along with transmitter, we also have an ultra-low power OOK receiver on the same chip that captures control signal from a nearby base station to achieve closed-loop control. The receiver consists of 2 stages of RF LNA, a differential to single-ended converter, or D2S, an envelope detector, or ED, 2 stages of baseband VGA, and a baseband comparator. The last major building block of the system is a controller to automatically choose optimal control policy. There are various ways to implement such a controller, and the comparisons are demonstrated in the table on the left. First of all, we may offload control tasks remotely to the cloud, or we may use a lookup table or use system emulator to select optimal policy on the edge. These control schemes either suffer from delayed environment accountability, policy learnability, or control latency. So to mitigate these challenges, we have chosen Neuro-based actor-critical controller. In the AC controller, there are actor and critic implemented with neural network. Actor will infer optimal policy, while critic will emulate the system during inference. During learning, critic neural network trains itself with emulation error and also provide backpropagation paths for the actor neural network to learn based on target error. Compared with aforementioned control schemes listed in the table, the edge control enables real-time adaptation, neural-based implementation enables learning, and single-shot inference maximally reduces the control overhead and the latency. The actor-critic neural network controller consists of 4 10x10 neural networks, 2 for critic and 2 for actor. Each 10x10 neural network is implemented by computing in memory block. When doing vector multiplication, the bit line discharge is controlled by DTC pulses and stored weight. Accumulated differential voltage drop is converted after sequential operation of bit lines. All storage elements are connected vertically and horizontally that enables in-memory forward and backward propagation for inference and learning respectively. Further, to account for extensive learning operations, the storage cell also supports time-based in-memory weight update. After bit line finishes discharging, ADC is used to convert analog voltage to digital for further computation. According to the data analytics of control problem computation showing on the right, we find most results fall in 6-bit range, while the worst case required 8-bit resolution, as shown in the figure on the top. As we know, ADC is a major power and area consumer, so we have chosen to implement an adaptive AD conversion scheme that uses lower resolution ADC for optimized energy efficiency, but still support 8-bit output. The circuit diagram is shown in the figure on the right. We choose 6-bit charge rate distributed SAR ADC and share the capacitors with the bit lines. This sharing improves the dynamic range and embeds the sampling process of ADC into the compute cycle. The ADC connect with weight storage elements vary at 10^1 mux. Further, we have 2 additional comparators that detect potential rate disturbance. When bit line discharge is below threshold, 6-bit ADC is converted first. Bit lines are array pre-charged. In addition, the monolithic switching procedure for ADC further reduces the energy. To enable in-memory update, the weights are encoded in a thermometer manner, and the mapping is shown in the table on the left. The weight storage element consists of 8 sequentially connected 1-bit storage cells, control logic, and a pull-up and pull-down transistor at the edges. The bit cells are so connected that it ensures that it allows only 1 bit line to discharge to improve dynamic range. The circuit for each bit line, bit cell is shown on the right. Compared with a conventional SRAM, it has additional word line transistor for transpose access and additional switches for in-situ data movement. This figure shows an in-memory weight update in storage element to increase magnitude. The pull-up transistor is enabled, right direction switch and data propagation switch on, and propagate 1 to the right for certain amount of time, t. Bit cells will flip 1 by 1. To decrease from a weight, 0 pass and the other direction is switched on as shown here. After the propagation, the storage element enters retention mode to store the new weight and vice versa. The weight update magnitude and direction is simply controlled by DTC-generated time pulses and data path configurations. And now I'm going to talk about chip characteristic and memory results. This slide shows a chip diphoto and the chip characteristics. This chip is fabricated in 65nm technology and total area of 5 mm². And among them, we can see that only 3% is consumed for actor critical controller, which is a small area overhead for the whole system. And this slide shows measured P array energy efficiency. In the figure on the left, it shows a maximum clock frequency as well as dynamic power across various supply voltage. For the clock frequency, we measure the maximum clock frequency of 730 megahertz at 1 volt. And for the power, we measure the minimum power of 1.4 milliwatt measured at 0.5 volt, 100 megahertz for sparsely connected layer configurations. On the right, it shows per operation energy efficiency for various configuration, convolution, fully connected, and sparse layers. Here we can see the minimum, the maximum energy efficiency, the optimal energy efficiency achieved by convolution layers of 0.95 per operation. As through energy breakdown, we can see this minimum energy is achieved by maximally reducing the SRAM access by putting a lot of SRAM, most of the SRAM in retention mode. And this slide shows a measured adaptive transceiver transmission efficiency. The figure on the left shows the transmission efficiency in percentage. We measure maximum transmission efficiency of 30% at around 0 dBm and at 1 volt. And on the right, it shows energy efficiency in picojoules per bit, and we measure the minimum transmission efficiency of 135 picojoules per bit at 1 megabits per second minus 14 dBm and 0.8 volt. And the in-memory computation accuracy is measured with real data. The gray bar statistically shows the probabilistic density of target computation result distribution. It shows that more than 95% of vector computation results in minus 40 to 40 range, which is consistent with our motivation to use adaptive 6-bit ADC. The arrows are shown with scattered dots. We have measured that with increasing computation final result magnitude, uncompensated errors, as in red, tend to be larger. An average of 1.6 is measured. This mainly comes from bitline leakage due to unbalanced zeros on both sides. The leakage error can be compensated in digital domain. After compensation, average error is reduced to 0.6. This slide shows the measured computing in memory module for the controller. On the left, it shows energy per operation for computing in memory module versus digital module at same bit precision. Operation of MAC and weight update are measured and compared. We've measured for our computing in memory module. It consumes around 0.6 picojoules for MAC and 0.4 picojoules for weight update, which is 2.2 to 4.75 times compared with digital. This energy saving comes from the fact, if we look at the energy breakdown, we can see that this comes from the fact that the computing in memory totally eliminates the memory access for both reading, multiplication, accumulation, as well as weight update. On the right, it shows the inference and per inference and training energy consumption across various supply power. And we measured 156.8 picojoules per inference and 305.2 picojoules per training at 0.7 volt. And this is a measured system level performance. On the y-axis is normalized energy and delay. Our proposed work is compared with the baseline design of 4-edge computation and 4-cloud transmission. And the test environment is modified AlexNet, 60 to 78 dB pass loss, 1 to 150 sensor nodes, and the bit error rate requirement of from 10 to the -3 to 10 to the -5. And we've measured 2.4 to 4.5 times energy savings and 1.5 to 2.2 times delay savings on average. This is a state of comparison with other work. The proposed system is one of the first prototypes to address computation and communication trade-off with full SoC solution. We have benchmarked our system with state-of-the-art designs and show competitive figure of merit with respect to system, computation, transceiver, as well as controller. The design presents a vertically integrated SoC featuring the first real-time N-based adaptation of computation, communication, and their trade-offs in energy-constrained systems. So to conclude, this is a wireless image processing SoC with online computation communication trade-off. And its DNN pipeline has a network-wise and layer-wise reconfigurability with peak efficiency of 1.05 TOPS per watt. And it has an on-chip real-time programmable adaptive transceiver with minimal 135 picojoules per bit transmission efficiency. And it has a self-learning, single-shot, and hardware-efficient on-chip controller with hundreds of picojoules inference and training, and only 3% area overhead. Thank you.